Welcome to lecture 28. So in the last class, we were talking about objectivity, right? And we saw that which of the quantities are objective and which are not. They're all basically kinematic quantities. Big F, for example, or U or V, right? And in the end, we were also looking at C. So C, we saw that it's equal to F transpose F, but then C star is then QF star, sorry, QF transpose into QF, and that became same as C. So C star is same as C. So therefore C star is not objective in the way we have the definition for objectivity, right? And the fact that C remains the same also tells us that the two motions, that is y of x comma t and y star, which is equal to q of t times y of x comma t plus c of t. So these two motions are such that they have the same strains in them. Longitudinal, you talk of longitudinal strain, change in angle, change in area, change in volume, they are the same. So the deformations are the same in the two motions, which is getting verified also from the fact that C is equal to C star. Okay. And also directly you can see that they are related through rigid body motion. All right. So having seen that, let us think of some more quantities. What is called convecting and co-rotating basis. Convecting and co-rotating basis. Okay. So what I mean here is that, again, suppose you have your body and which has gotten deformed, and think of a particle and having three material lines. Okay, so these you can say they are, for example, F1, F2 and F3. So these are material lines which will have some image in the reference configuration also. So F1, F2, F3 are the current material lines. Okay, and as the body deforms, these material lines are also deforming, isn't it? And and we have seen that these material lines, the rate of change of these material lines is such that Fi dot is equal to L times Fi, isn't it? Okay. Now, suppose that there is a vector V, or let us say a vector A, and you are sitting in the body, you are sitting in the body at this particle P, and with those bases F1, F2, F3. Okay, and you measure the vector A. So let us suppose we are sitting in a frame having F1, F2, F3 as basis vectors. And then we obtain the components of A in this coordinate system. Okay, so as time progresses, these basis vectors, we see that they convect with the body. So that's the meaning of convecting basis. As the body is deforming, these basis vectors are also deforming with the body. So it is convecting with the body. So it's a convecting basis. So suppose I define the component of the vector AI in this basis. That becomes AI, which is equal to the vector A dotted with Fi, isn't it? And then let's find out the time derivative of this component. So when you are sitting in this frame and then you want to find out how are these components changing with time, okay, while sitting in this frame itself. So what will then be ddt of AI? So that's simply A dot product Fi plus A dot product Fi dot, isn't it? Okay. Um, but Fi dot is L times Fi, so we can write it as A dot Fi. Okay, so this is then plus A dot L Fi. Okay, and you can bring this L on the other side, and then what we have is A dot plus L transpose A times Fi, isn't it? Sorry, dot with Fi. So what we see is that d by dt of AI is equal to A dot plus L transpose A dot with Fi. So what can we infer from here? That this time derivative of the component is actually the ith component of this vector on the right hand side, isn't it? And you'll see that in the book, this time derivative of the component, they denote it by AI with a triangle above. AI with a triangle above. And I'll tell you just now why it is so. AI with a triangle above is equal to A dot plus L transpose A dot with Fi. So this, by the way, is section chapter 3.9 in the book. So from here, then you can think of a vector A triangle, which is equal to A dot plus L transpose times A. Okay. So this vector A triangle, you see, it is not the same as the material time derivative of the vector A. So this A triangle, this is called convective time derivative. Convective time derivative. See, we didn't call this thing over here, we didn't say it is AI dot, because from here it looks like, I mean, this is AI dot, right? But we didn't call it because this is not equal to the ith component of A dot. You can see from here, right? From here, what you see is that this is equal to A dot ith component plus L transpose A ith component. So you can see that this is not equal. So if we had written AI dot, no, then we could have confused it by thinking that it is actually the ith component of A dot. So therefore, we are calling it AI with a triangle above. Okay. Likewise, you can also think of the similar thing for a second order tensor. So suppose you have a second order tensor A, and I represent this in this convecting basis, Fi tensor product Fj. Okay, which also means that Aij is equal to A times Fj and then dot with Fi. Okay, so what is then d by dt of Aij? So we simply have to take then the dots on all the three vectors on the right hand side, and we get A dot Fj dot with Fi plus A Fj dot with Fi plus A Fj dot with Fi dot. And then we know that Fi dots are L times Fi. So this then becomes A dot Fj dot with Fi plus A times L of Fj dot with Fi plus A Fj dot with LFI. Okay, and this then finally becomes A dot plus EL plus L transpose A of Fj, and then the whole thing is then dotted with Fi. Okay, and so on the left hand side, what we have is, we will again denote it by a triangle, Aij triangle. So it's the time derivative of the convecting component. So we can say that it's a time derivative of the convecting component of the tensor A. And so from here we can then say that there is this tensor A. So the convecting time derivative of this tensor A is then equal to the material time derivative A dot plus EL plus L transpose A. Okay, and we'll just see why are these time derivatives important. It's important because it turns out these time derivatives are objective. So let us suppose A is an objective tensor. Okay, let us say A is an objective tensor, or let us first of all start with the vector A. Let us say vector A is an objective tensor. So this implies A star will then be equal to Q times A, right? So what is then A star dot? So A star dot is simply Q dot into A plus Q times A dot. Okay. So if somebody asks you, is A dot objective? Then what will your answer be? Is A dot objective? So for objectivity, the definition is that A dot star should be equal to Q times A dot, right? But is that holding here? So that's not holding, right? So notice that if A is objective, that doesn't mean that its time derivative will be objective. But what about the convecting time derivative? Let us see what's happening to the convecting time derivative. So A triangle is A dot plus L transpose A. Okay, so let us see, is this objective or not? So this implies A triangle star will be equal to A dot star plus L star transpose into A star. Okay, so now what is A dot star? So from here you can write down what is A dot star. That's Q dot into A plus Q times A dot, okay, plus L star transpose. So what is L star? I think we had earlier seen that L star is equal to, I believe it was equal to Q transpose plus, there was something more. Is it Q dot Q transpose? So we then put it here. So we have to write L star transpose. So that is then Q L transpose Q transpose plus Q into Q dot transpose. Okay, so this is L star transpose, and this then gets multiplied with A star. But A being objective, A star is then simply Q times A. If A triangle has to be objective, then this should be equal to Q times A triangle, right? And A triangle is the definition up here, which is Q times A dot plus L transpose A. So we should be able to show this. So does it look like it is that? So here we have Q dot A plus Q times A dot plus, now look at this combination. This is indeed Q times L transpose A. And then we have the final one plus Q times Q dot transpose into Q into A. Okay, so that is a bit different one. So we have to think what to do with this. So you can see that we have these two terms which are exactly as it is here. So perhaps we have to cancel. These two should cancel somehow. So let us see if we can do that. Okay. So we have Q dot A, that's, we can write it as Q dot Q transpose into Q into A, right? Which we can also write as Q into Q dot transpose and then transpose into Q into A, right? Because when you do the transpose, you get back what you have above. But you see that Q dot transpose, that's a skew symmetric tensor. So Q dot transpose is skew symmetric because Q is a rotation, no? So that means Q dot transpose will be same as minus of Q dot transpose times Q times A. And this is, you can see that it's same as this. So therefore those two cancel, and finally you are only left with these two terms, which indeed means that the convecting time derivative is indeed a objective time derivative. So that's the importance of convecting time derivative. Material time derivatives are not objective, but convecting time derivatives are objective. So, later on you will see that when we are talking about constitutive equations, then often the material is such that the constitutive equation also has the time derivative of some vectors present in it. Okay, for example, you may have the tensor sigma. A simple elastic material sigma would be equal to some function of strain, but if you have viscoelastic material, you may have sigma in the constitutive equation. So in such cases, if you have sigma dot, then you can't, what objectivity tells us is that since the constitutive equations have to be objective, you cannot have sigma dot in the constitutive equation. You must have either the convecting time derivative or any other time derivative which is objective. You can't have sigma dot. So that's a way to rule out that sigma dot cannot be present in the constitutive equation, because all constitutive equations must satisfy objectivity. So we'll talk more about this very systematically in the next lecture, okay? But the importance is that these time derivatives, the convecting time derivatives, are objective time derivatives, okay? And they figure in the constitutive equation, not the material time derivative. Okay, so this was for showing the convective time derivative of vector. Likewise, you can show that the convective time derivative of a second order tensor is also objective. Okay. So just like I said, just now you're saying that if sigma is there in the continuity equation, then you can't have sigma dot, but what you can have is convecting time derivative of sigma. That means you will have this term together appearing in the continuity equation. Okay. Likewise, we also have the concept of what is called co-rotating basis. Co-rotating basis. So in this case, we think of that we have the body and then we are at a point P, and then there are three vectors which are not engraved in the body, by the way. If it were engraved, then it becomes a convecting basis. But these vectors are attached to the body in such a way that they are just rotating with the body. That is why it's called co-rotating basis. So they just rotate with the body, which means that Fi dot is simply the spin tensor W times Fi, or omega cross Fi. Okay, so W is a spin tensor because it's co-rotating with the body. That's why you get W here instead of big L. Okay, so when you talk of, it turns out that the co-rotating time derivatives are also objective. Okay, you can, for example, show that just like we worked out f of the co-rotating time derivative, we denote by a with a circle. Okay, so this is to denote co-rotating time derivative. So this will turn out to be equal to the material time derivative of A minus W times A. Okay. Contrast this with the convecting time derivative. We had A triangle is equal to A dot plus L transpose A. Okay. So instead of L, you will now have, for co-rotating, you will have W. So it is A dot plus W transpose A. But W being skew symmetric, you get a minus sign therefore. Okay, so that's why the co-rotating time derivative look like this. And similarly, you can show that the co-rotating time derivative of a second order tensor is material time derivative plus A times W minus W times A. Okay. So these are the two rates which are objective. There are many other rates which are also objective. Okay, and if you want to know about them, you can look at the worked out example here. I'll just tell you which one it is. So problem 3.18. So look at problem 3.18. It is already solved in the book. So you will see that there are two more time derivatives introduced there. Now you see, finding out whether these quantities were objective or not was easy. You simply apply the formula. And these were kinematic quantities, so you knew how they were transforming. What was, for example, look above. What was, for example, C star? You could know it because this was a kinematic quantity. So it was quite easy to find out what is C star. Similarly, what is F star, what is V star, what is U star, it was easy for you to find them because you had the kinematic relation. But what about the quantities which are not kinematic, and how do we say whether they are objective or not? So for them, you have to postulate. For example, I think many of us started with, we said what could be objective quantities, and you straight away said that density would be an objective quantity. Right? Many of you said density is an objective quantity. Similarly, many of you said temperature is an objective quantity. But what was the basis for you to say that? That was simply based on physics, isn't it? So indeed, for quantities which are not kinematic in nature, we have to postulate for them. Okay. So I'll just write that here. Let me change the color. Quantities which are not kinematic we have to postulate for them. That means we don't have a mathematical proof, we simply postulate based on physics. For example, rho star, we would say that it is equal to rho. So for the two motions, the density, it is quite clear, no? Because they are related to rigid body motion. So rho star must be equal to rho, right? Similarly, theta star must be equal to theta. It won't affect the temperature distribution because they are related through rigid body motion, isn't it? Likewise, your internal energy density, for example, epsilon star, that must be equal to epsilon, right? Similarly, the heat flux H star, that must be equal to H. Likewise, the heat generation rate per unit volume, R star, that must be equal to R, isn't it? So these are based on physics because these are not kinematic quantities. Okay, and then for traction, you remember that we have this body which undergoes this motion y, and it is like this, and in y star it may be like this. So it has to look the same, by the way. So let me try to be somewhat more accurate. Yeah, so here then at a point P should have been here. So if the normal is over here, the corresponding normal will be here. So whatever is n here, that becomes n star over here, right? And the traction T here, that becomes T star. Now, because it's a rigid body motion, so you can guess that the T star and T must be related by that Q, isn't it? So T star, so this is again based in physics, that T star must be equal to Q times T. And likewise, N star would be equal to Q times N. This is based on geometry, right? Because the body has rotated, so the corresponding normal must have also rotated. So let us now think of what about sigma? What is happening to sigma? So suppose sigma is sigma star. So we know that sigma star times n star is then equal to T star, right? As per the definition. But this is equal to Q times T. And n star we have just seen it is Q times n. So that means sigma star times Q times n is equal to Q times T. Okay. Now if you bring this Q on the other side, then you have Q transpose sigma star times Q times N, that's equal to T. But then this thing inside the bracket must be sigma, right? And then from here you can see that sigma star is indeed Q times sigma times Q transpose. So we are able to prove that sigma is objective, right? Based on the physics for the traction and from the geometric relation for n star. We are able to prove that sigma must be objective. Okay. Similarly, you can show that the stress power, for example, is also objective. See, what is stress power? That is, if you talk of per unit undefined volume, then it is J times sigma double contraction T. Now, J is an objective quantity. You see, J is a scalar, which is determinant of F. Then J star is then determinant of Q times F, right? Which is same as determinant of Q into determinant of F. But Q being a rotation tensor, determinant of Q is equal to 1. So this is same as J therefore. So each of the quantities here are objective. J is objective, sigma is objective, and D is also objective. So if you try to find out J star times sigma star double contraction D star, then this is equal to J Q sigma Q transpose double contraction Q D Q transpose. Okay, and then through some, you can go back to initial notation and indeed show that it is equal to J times sigma. Then if you talk of heat flux vector, what will heat flux vector be? Will it be objective or it will not be objective? So for that, we just postulated above that H star is equal to H, right? Now H star is will be Q star dotted with N star, right, from definition, which is equal to Q dot N, but N star is equal to Q times N, big Q. So that means Q star dot with Q times N, that's equal to Q dot N. You bring this Q on the other side, so you have Q transpose Q star dot with N is equal to Q dot N. And since it holds for every N, you can say therefore that Q transpose into Q star is equal to Q, or Q star is equal to big Q times small q. So therefore, this heat flux vector is also objective. So likewise, you can show it for several things. Okay, and I won't do all of them because some of them will come in the what is called exam. Okay. So I hope that this objectivity is clear to everyone and why it is important. You somehow have this feeling that it will come in the, it's important from the point of view of constitutive equation, but it will become more clear as we actually talk about constitutive equations from the next lecture. Okay, let me do another solved example since we have some time. And this is from the book also. Yeah, I think somebody has a question. How is sigma double contraction D? Okay, proof. All right. Okay, maybe I can do a side calculation here. So sigma star double contraction D star. This is same as sigma ij dij. Sorry, sigma star ij D star ij. Right? Double contraction, that's the meaning. And sigma star is Q sigma Q transpose. And then take the ij component into Q D Q transpose and take the ij component. Now, what's the ij component of this thing? This will be Q I M sigma M N into Q transpose Nj, which is same as QJN. Okay, whereas from here you'll get QI A D A B into QJ B. Okay, now it's quite easy now. See this QIM into QIA, and then you have QJN into QJB. What are they? The fact that Q is a rotation tensor, QIM into QIA, that's delta MA, Kronecker delta MA, whereas this one is Kronecker delta NB. So it finally becomes Kronecker delta MA sigma MN Kronecker delta NB DAB, which is same as, now look at this one, this is equal to sigma times AN, and this is then equal to D times AN, right? And isn't this same as sigma double contraction D? Is this, is that okay, Nilesh? Okay, very good. Now let me do a solved example. Um, this is problem 5.3 from the book, by the way. Well, it is not solved, but it's a problem in the book. Problem 5.3. So you see, we have as of now the equations of motion, that is divergence of P plus J times B is equal to rho naught times acceleration. That's of course in the Lagrangian form. So it has three equations, and then we also have the the first law of thermodynamics. And can someone tell me what was it in the Lagrangian form? So that's rho naught into R minus, and this is of course the Lagrangian divergence, no? And here again you have Lagrangian divergence dot Q naught plus P double contraction F dot, that's equal to rho naught times epsilon dot. Okay, and if I want to write this in terms of Helmholtz energy, then it is rho naught times, so psi was equal to epsilon minus eta into theta, so epsilon becomes psi plus entropy eta times theta, and then we have the time derivative. Okay, so this, of course, this question I should have done it after I have worked out the constitutive equation. But just because we have been doing theory and many of you are thinking how to apply this. So you see that we have this set of four equations. We have four equations, but there are so many unknowns. Okay. So later on you will see that the constitutive equation is such that one can think of a Helmholtz free energy psi as being a function psi hat of deformation gradient f and temperature theta. And from here, when you put it in the second law of thermodynamics, the entropy equation, it will give you that the first Euler-Kirchhoff stress tensor P is actually the derivative of psi hat with respect to deformation gradient f. So you see that, like I was telling you, that once you have this energy form prescribed, then second law of thermodynamics can tell you about the constitutive equation, and this is what it is, that P turns out to be the first derivative of psi hat with respect to deformation gradient. And likewise, the specific entropy eta, that turns out to be negative of derivative of psi hat with respect to theta, temperature. Okay, and there's a Fourier law for the heat flux vector Q naught, referential heat flux vector Q naught, which tells us that this would be equal to a tensor K, which is a function of deformation gradient big F and temperature theta, and multiplied with the Lagrangian gradient of theta. So these are, like your constitutive equation for P, for specific entropy, and for Q naught. So now you see that P is in terms of kinematic quantities, which is your deformation y hat, and theta can also be thought of as a unknown variable, independent unknown variable. So if you now look at this equation, for example, P is now in terms of y hat and theta. So P is no more an independent variable. P is something which will be prescribed to you because it's an externally applied body force. Acceleration is, again, you know that this is del 2 y hat by del x2. So it's a function of, del t2. So it's a function of second derivative of deformation. Then again, this r here, this will again something that is prescribed to you. Okay. So it's not an independent unknown. It's not an unknown anyway. Now Q naught, you again have the constitutive equation for Q naught, so it is no more an unknown. Likewise, P, we said that it has a constitutive equation, and then here psi is prescribed to you, right? You said that there is some psi hat, so psi function is prescribed to you, it is known to you. Eta, again you have constitutive equation, and theta is an unknown. So what you see is that with these constitutive equations prescribed, you only have y hat and theta as the unknown. So there are four unknowns, right? Because y hat has 3. So 4 unknowns and you have 4 equations. And that is how you can solve. You can see that it's the constitutive equations which provides the missing equations and hence makes the system closed. Okay? And you can in fact, put these constitutive equations back in the equation and explicitly work out the equation in terms of y and theta. So that is something you should work out. Okay, I might give this to you as an exam. Okay, so I think with this I will stop the class.